you all to this colloquium of today. I'm really pleased and honored to introduce our guest of today, Professor Mihalis Dafermos from Princeton University, and also a Lowndean Chair of Astronomy and Geometry at the University of Cambridge. Let me say a few words about him. He got his bachelor degree at Harvard University, and then his PhD degree at Princeton under the supervision of Demetrios Christodoulou. And then he held various appointments at Cambridge and joined the Princeton Faculty of Mathematics since 2013. And since 2015, he also joined the Department of Pure Mathematics and Statistics in Cambridge. He has received various awards. Let me just mention Adams Prize in 2004 from the topic differential equation, the Whitehead Prize in 2009 for his work on the rigorous analysis of hyperbolic partial differential equation in general relativity. He was selected in 2016 as Fellow of the American Mathematical Society, and he was invited speaker at ICM in Seoul in 2014. He is well known for his fundamental contribution in general relativity and in partial differential equations, in particular in the analysis of the formation and stability of black holes, as is discussing today, and the structure of cosmic singularities. I am really pleased that he is a guest today. Please.
So can everybody hear me? Okay. So first of all, thanks very much for that introduction. It's an incredible honor to be speaking at this university. It's a very old university and one with very old links, at least with the University of Cambridge. I don't know. With Princeton, and one very connected to mathematical physics in general, but in particular to general relativity. After all, this is a department, I guess, named after Tullio Levi-Civita, who will appear in this talk. So the title, I hope, isn't going to worry anybody on falling into black holes. Let me tell you immediately a summary of this talk, and then we can begin. So I'll give a maybe it's better here. I'll give a short crash course on general relativity. It will be incredibly short, but hopefully it will be sufficient to understand what I really want to talk about in this talk, namely black holes. So the issue that I want to talk about actually pops out very naturally from comparing the geometry of the two most celebrated black hole solutions of general relativity, the so-called Schwarzschild and Kerr black holes. And the question that pops out of this is the so-called strong cosmic censorship conjecture. So this is a conjecture due to Roger Penrose. And the main result, if you want, of this talk will be a slightly unsettling theorem that I recently obtained with a collaborator, Jonathan Luke of Stanford University. And finally, we'll end in a Leninist note, what is to be done after all this. Okay, but first things first, let's begin the crash course on general relativity. And I really tried to take this from the beginning. So of course, in pre-relativistic physics, we learned that there is space on the one hand, and there is time, and these are separate things. This is a Swiss railway clock. I didn't try to use an Italian railway clock. It's not necessarily so accurate. So the first thing that we are taught in relativity is that, space and time are not separate. So of course, this idea is associated with Einstein in 1905. Actually, many other people contributed before Einstein to understanding this. But the sort of definitive understanding of what replaces space and time as separate entities was actually attained by Minkowski. And it's to Minkowski, around 1908, that we have the notion of space-time. So what is space-time? Well, okay, let's begin with flat space-time. This is the space-time that Minkowski introduced. Well, of course, okay, naively, it is just you add the time dimension to space, and you get sort of a four-dimensional continuum, R4. Okay, but of course, if it were just this, then there wouldn't be much point in giving this a name. Together with R4, Minkowski understood that there's a structure. Let's go back. Namely the structure of a light cone. So this is actually from Minkowski's 1908 paper. And this principle that Einstein first understood, namely that the speed of light should be the same in all allowed coordinate systems, Minkowski understood in the sense that a certain cone is objective in space-time. Okay? So this is precisely the cone that is depicted here. Of course, I have to always suppress one dimension when I draw space-time. So, okay, we can use our imagination to think of this as R4. Okay? So if you think about it, this cone denotes sort of the all the points which are sort of starting from this point. It denotes sort of all the trajectories in space-time, okay, which travel at what we think about as the speed of light, okay, and this c here, okay, is the speed of light in some units. Okay, so this is what Minkowski first understood, that sort of actually, instead of thinking of the speed of light in reference frames, we should think about cone in space-time. And in fact, we should really only think about the cone in space-time. So first of all, at every point you should think there's a cone, okay, that sort of delimits the speed of light at each point, okay? And we should only think about the cone. So we should forget about coordinates t, x, y. We should just think there's this space-time continuum, and at every point there's a cone. Okay. So this is special relativity. Okay, what else can we understand? So again, we're in Padova, so we should be able to understand inertia, right? So what are inertial observers in special relativity? They are just the trajectories of straight lines in space-time. So these are so-called world lines. So think of this as an inertial observer moving through space and time. But there's an extra kinematic constraint. Okay? And this is precisely what Einstein originally formulated, that no observer can travel faster than the speed of light. So you see this here. These straight lines are always confined, okay, to be inside the light cones. Okay? So the tangent to the line at every point is always in the interior of the light cone. Okay? So this is sort of part of the structure of special relativity. So the last thing is, okay, so what sort of characterizes straight lines? What makes them distinguished? Well, Minkowski also sort of defined this notion of proper time. So this is described by this sort of length element, but with a funny sort of signature. And so proper time, so this element here allows you, upon integrating it, okay, so you can integrate this expression along any curve, so in particular along any line, okay, and you get a number, and this is the so-called proper time. So this is the time experienced by this observer going across this world line. Okay? So this implements, again, the idea of Einstein that the notion of time is relative. So every observer, so here's one observer, here's another observer, okay? every observer, they have their own proper time, okay? And so this, I depict in this picture. So this is an observer with a German railroad clock, and this is an observer with a Swiss railroad clock. And in all cases, the railroad clock runs by integrating this expression, this differential expression from this point to this point. And the straight lines, you can characterize them in terms of this geometry. They are the curves which maximize proper time. So this is sort of funny. It is opposite to Euclidean geometry, where straight lines minimize length. Okay? In this geometry of Minkowski, the straight lines whose tangent are inside the light cones, they maximize length. Okay? So in particular, if you consider a broken straight line like this and like this has less proper time than this. Okay? And this is exactly what gives rise to what's known as the twin paradox in special relativity. Okay. All right. So this is flat space-time. This is the geometrization of special relativity due to Minkowski. How does one incorporate gravity? Okay? So in particular, how does one incorporate the motion of freely falling observers in a given gravitational field? Okay? So that would be the analog of sort of this equation, okay, for a given gravitational field F in Newtonian theory. So Einstein tried very hard to find a sort of special relativistic version of this equation, but he was not able to, and finally what he understood is he had to sort of generalize this sort of notion of space-time of Minkowski further. So how did he do this? And this was sort of a very insightful leap. He sort of passed to a notion where space-time is curved. Okay? So what does this mean? Well, what you should think is this means that these light cones at every point of space-time, they are now sort of oriented in some funny ways with each other. Okay? So what is the mathematical embodiment of this? Well, for this, Einstein needed a little bit of help, and fortunately, his former classmate Marcel Grossmann was indeed there to help him. So this is Marcel Grossmann. This is Einstein around 1913 when they wrote this joint paper together. So he's a bit older than he was in the other picture of him. So basically, that metric, that notion that gave us proper time of Minkowski, the idea is you make this now, you allow this to depend on the space-time point. Okay? So this is sort of what defines a curved space-time. So Einstein and Marcel Grossmann were very fortunate that this mathematical structure that they needed, it was already available. It's exactly the structure called Riemannian geometry. Okay? The only difference is that the signature of this metric should not be what we now call the Riemannian one. It should be minus plus 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 or plus minus 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 equivalently. It should be the signature of Minkowski's spacetime. Now, nowadays we think of Riemannian geometry as a big field in mathematics. But in those times, there were essentially only two people working on that field. And both of them were here in Padova, Ricci and Levi Civita. And we will meet them again in just a few slides. But in particular, it was from their famous paper, Méthode de calcul différentiel absolu et leur application, from which Einstein and Marcel Grossmann learned the structure of what was then called tensor calculus. Okay? So how does this, how can you hope that this idea of bringing in sort of differential geometry or sort of curved space-time, how can you hope that this can capture freely falling particles in a given gravitational field? Well, the postulate is that freely falling observers in a curved space-time, okay, should follow curves which locally maximize the proper time. Okay? So remember, in flat space-time, straight lines, which are the inertial observers, okay, Galileo, the inertial observers, they followed straight lines, and straight lines, again, in Minkowski space-time, they can be characterized as maximizers of proper time. Okay? So the idea here is that, again, you postulate that freely falling observers in a given gravitational field, okay, they traverse curves in space-time that maximize locally, okay? So this just says extremize, but it turns out with this signature, they will maximize locally proper length. Okay. So of course, these are the generalizations of geodesics in the geometry of curves, except now the signature is this funny one, and so instead of locally minimizing, they locally maximize. Okay, so this was sort of really the inspired step of Einstein with the help of Marcel Grossmann. Okay, this is great, but what determines somehow the curvature of space-time, or what determines this sort of funny metric that supposedly governs the gravitational field? Because remember, in Newtonian gravity, okay, we don't just have this law that says that if the gravitational field is F, then particle moves by this equation. We also, okay, have a relation that tells us what F is given all the particles you have in your universe, right? So we saw the analog of this. Okay, this is just sort of motion along, let's call them geodesics, so these time maximizing curves. But what is the analog of this? Okay, so first of all, Einstein very early understood that, I should say as an aside that the first person who really was trying to find a relativistic analog of this in this form was actually Poincaré. But Einstein understood very, very quickly that you cannot try to say this with point particles. You really have to think about fields. Okay, so remember, a better way of thinking about the Newtonian theory in the context of field theory, right, is that you have a continuous distribution of matter. Let's call it rho. Okay, so you have the gravitational potential, okay, satisfying the Poisson equation. Okay, and then F is just given by minus m times the gradient of phi. Okay, so you can see actually this is taken from Einstein's paper with Marcel Grossmann that we are, anyway, I don't know any German, but I infer this says that we're looking, in other words, for a generalization of the Newtonian equation, this. And actually, Einstein struggled with this quite a bit, and in his paper with Marcel Grossmann, they could not, well, they tried to find a generalization of this, but it was totally wrong in some sense. So, but Einstein came back 2 years later, and he got it right, and this is his famous paper of November 25th, 1915. So here's some German, which I don't understand, so let's get rid of it. So in that paper, you'll see these equations, and these are the celebrated Einstein equations. Okay, so as I said, you should think of this as a generalization of sort of the Poisson equation for the Newtonian potential, with the right-hand side sort of the mass density of matter. Okay. Equations have a left-hand side and a right-hand side. So the left-hand side, okay, is some measure of the curvature of space-time, so how curved these cones are with respect to each other. We'll get back to the left-hand side in just a second. And the right-hand side is some measure of the energy, momentum, and stress of matter. So already, those of you who know special relativity, you all know E equals mc squared. So you all know that anytime you talk about mass, you also have to talk about energy. Okay, so on the right-hand side, whatever's on the right-hand side, okay, it could not possibly just be mass density, because depending on sort of the frame, right, you also have energy. But actually in field theory, it is not only mass and energy that are unified in relativity, even in special relativity, it is also stress. Okay? So that's why the thing on the right-hand side is this higher order tensorial object, okay, that unifies stress, energy, and mass, okay, and momentum. Okay, so okay, so this is what's on the right-hand side. So let me make so if you want, okay, this is this sort of picture. So people like apples when they talk about gravity for obvious reasons. So you think of the apple as being some matter which is curving space-time. Okay. Let me make some comments before we continue. So this is actually not the way we typically write the Einstein equations anymore. So actually, I think it was first Levi-Civita who realized how you should write these equations. So if you replace G with something which he denoted A, okay, these equations simplify to this form. Okay, which you could rewrite AIK equals, well, with this convention, minus TIK. So this is actually the way that we write the equations now, except that this is so much better that what he denoted A is now denoted G. Okay. Now, what Einstein denoted G is now denoted R. And this is a fake picture because, fortunately, Einstein also had an R in his paper, but it meant something else. So so historians beware. You will not find this. I've actually pasted two things together, both from his paper. Okay. But it's actually very convenient that it's now denoted R, because actually this part of the curvature, okay, is exactly what's now known as the Ricci curvature tensor. And this was first written down by Ricci already in 1903. Okay? So Padova is everywhere in the Einstein equations. Okay. So I'm going to keep on using R, but beware, all my pictures are sort of whatever. They're fake. Okay. I'm from Greece, so we know how to fake data. All right. So, okay, so all this is very familiar. So let me tell you something that often is not emphasized enough, but which is extremely important and extremely ironic historically. So it turns out the Einstein equations are non-trivial even in vacuum. So even if there is no energy, momentum, matter anywhere in space-time, so in that case the equations take this form in the, okay, with my fake pictures, the Einstein equations are still non-trivial. So that's to say we can actually get rid of the apple, okay, and the space-time can still be non-trivially curved, okay, and the reason is that the Ricci curvature tensor is only part of the curvature, okay, it is not the whole curvature. That's the whole point of the Ricci tensor. It is part of the curvature. So space-time can still be non-trivially curved, even though there's no matter anywhere. And you should think that this is related to the nonlinearity of the equations. So my academic grandfather, Johnny Wheeler, used to say that space tells matter how to move, and matter tells space how to curve. But actually, space also tells space how to curve. And this will be very useful in the rest of the talk. The reason is that it is much more difficult to understand the equations of matter than it is the equations of gravity. So even though this equation here has a reputation of being something very complicated, it is actually easier to understand than the equations you'd have to couple this to if you wanted to understand matter. So there will be no more apples in this talk. So the Einstein equations are non-trivial, even in vacuum, And in fact, curvature propagates in vacuum as a wave. Okay, so you can see it propagating away as a wave. And, well, very famously, these waves, which actually were first predicted by Einstein, even though Einstein later retracted his prediction. It's a complicated story. In any case, these waves have now been directly observed on Earth by LIGO and now also by Virgo in Pisa, I guess. So, so this is something that we really believe is reality. So, so it turns out that secretly this fact that the Einstein vacuum equations have this sort of wave aspect to it, what it was secretly telling us is something that it took a while to understand correctly mathematically. But what it was secretly telling us is that those equations are hyperbolic. Okay? So they are nonlinear hyperbolic. And proof of something being nonlinear hyperbolic is that it should have a well-posed Cauchy problem with the so-called domain of dependence property. And this was something which was proven in 1952 by Yvonne Choquet-Briard, then called Furet-Briard. So what she proved was that just like the equations of Newtonian dynamics, for the Einstein equations, there's an appropriate notion of initial data. So you should think of it as, space and the velocity of space at an instant. Let me not try to say that more precisely. And given appropriate initial data, there exists a unique solution to the Einstein vacuum equations, Ricci curvature equals 0, at least for small or short amount of time. And again, I put time in quotes because, well, as we saw, the notion of time is sort of observer dependent. So, okay, let me not try to formulate what short time means now better. We'll see in practice what it might mean. Okay? So this theorem is actually the theorem that's telling us that gravitational waves are real in the sense that they are a real prediction of the equations. Okay? And now we know that, well, they are an aspect of our physical reality. Okay? So this is coming from here. And somehow what this theorem also tells us, and this is important to always remember, is that even though this theory has a reputation of being something very strange, it is actually a quintessentially classical theory. Okay? In the sense that, at least for a short time, okay, initial data, there's some notion of initial data, and given initial data, you can uniquely predict, using the theory, what happens for some short time. So just like in Newtonian dynamics of point particles. Okay. All right, so that's basically the crash course. Let me just end with a summary of the crash course before we continue. So general relativity, first of all, space and time as separate objects are replaced by space-time. So, okay, in the modern view of space-time, we think of the continuum itself as being a four-dimensional manifold, but I should emphasize that notion actually came slightly later. So those of you who know what it is, good. If you don't, okay, just think of it as some four-dimensional continuum on which there's this, okay, what we now call Lorentzian metric, but you should think it's just this funny metric which defines at every point a cone, except the cones are sort of curved, all right? And freely falling particles in such a metric, they traverse geodesics, and geodesics are just locally length maximizing curves. Okay, so I should say proper time maximizing. We sometimes interchange the words length and proper time, okay? Which are always constrained to be inside those cones. And remember, that was the postulate that nothing moves faster than light. Okay, so that's the kinematics, but there's also an equation for the metric, so for the curvature of the metric given the energy momentum tensor of matter. And as we saw, this equation is non-trivial even in the vacuum case. And moreover, this equation admits a well-posed Cauchy problem. Okay? So this is really the way we think about general relativity as a theory. Okay? All right. So that's the crash course. Let's now try to understand what are black holes. Okay. And we'll understand this by looking at the so-called Schwarzschild and Kerr spacetimes. So the Schwarzschild spacetime was discovered only months after the formulation of the Einstein vacuum equations. So it was published in January 1916. If you remember, Einstein's paper was November 25th, 1915. But actually, this was discovered already in December of 1915. Okay, so it was really weeks after Einstein's paper. So this is Schwarzschild. This is some German. This is the metric that he wrote down. And this is the metric slightly bigger. You can, if you know the formula for Ricci curvature, you can a posteriori check relatively easily, although it probably will still take you the rest of this lecture. But this is a solution of this equation. So this was the first non-trivial vacuum spacetime to be discovered. So let me rewrite it in my own text. So it's written like this. One thing that sort of was immediately noticed is the following. So, okay, you can write this expression. You can write this expression for any value of A. A is a parameter, okay? And anyway, you should think of A as being something positive. Note, if A is equal to 0, this is just the Minkowski metric written in spherical coordinates, okay? So A is a parameter. And one thing that you notice immediately is that this expression looks sort of strange when r equals 0. So when r equals 0, so A over 0, let's say A is positive, A over 0 blows up. So this coefficient blows up. That's not good. If r equals A, well, you can look at this coefficient here. So you'll have 1 minus 1, 0, 1 over 0. That blows up. That's not good. And okay, if you were very consistent applying this logic, you might also say that if theta equals 0 or pi, then this also looks strange because, well, this looks like it completely degenerates, right? If theta is 0 or pi, this vanishes. Now, of course, no one ever said anything about this because people are trained when you see this expression here, you understand that this should be defined on the sphere. Okay, and this is just the spherical metric, and nothing's wrong with the spherical metric at theta equals 0 and theta equals pi. It's just that spherical coordinates degenerate. So everyone knew that, obviously, and no one was ever confused about that or even mentioned that. But actually, that's exactly the same thing that happens at r equals a with this expression. And even though it's not so difficult to realize that, this actually was not understood immediately. So this is the sphere. So the person who first understood this was actually Georges Lemaitre. So this text is taken from a paper which I'll tell you about in just a second. So it was Georges Lemaitre in 1932 who understood that this sort of apparent singularity at r equals a can be made to disappear by transformation of coordinates. So what I'm going to show you is how you should think about the geometry of Schwarzschild, but the way to think about a sort of a Lorentzian geometry is to draw the light cones. Okay? So we're going to understand what Schwarzschild actually looks like by drawing the light cones. Okay? So this is Lemaitre, very deserving of all these medals for this and for other things that he did. So anyway, this is how you can rewrite the metric so as to make the apparent singularity at r equals a disappear. But the way you should picture it is by picturing the light cones. So I've drawn here the light cones at every point in this metric. Okay? And you should think that the coordinates are r, which you should think of as the normal sort of r. Okay? And a new version of time, which is denoted, which goes up. Okay, so this is the, I shouldn't even call it time, so let me just call it, let me just call it taf. It's the Greek letter taf, which goes up. Okay, and in these new coordinates, you can write the metric like this. Okay, so anyone interested can check that this is the same metric by change of coordinates. But I will just describe to you what the light cones look like. So if you're very far away around where r equals infinity, so r equals infinity is there and there, okay, then the light cones are just like in Minkowski space. They're upright. Okay? So what happens in this geometry is that the light cones, as you move in towards r equals a, okay, as you move in, they're turning inward. And they're turning, so much so that when r is exactly a, the light cones are tangent to r equals a. And if you go further in, then the light cones have completely tilted inward. So what does this all mean? Well, think about freely falling observers. So remember, freely falling observers, they go along geodesics of the metric, okay, so locally proper time maximizing curves, which are constrained, however, to always be inside the light cone. Okay? Inside the light cone. So imagine two such geodesics. So imagine, so one is wise, okay, and follows this path here. So let's call him, I don't know, Fabio, for instance. That's the name. And another is sort of less wise. Let's call him Mihalis. Okay? So, so as you can see, Mihalis here can send a signal to Fabio because light rays, so this is another postulate of general relativity, okay? They travel tangent to these cones. Okay, so you see this signal, it's going off from Mihalis and reaching Fabio, okay? Along directions which are always tangent to light cones. Okay? But once Mihalis passes this point here, okay, any signal he tries to send is going to smaller and smaller r because the light cones have turned in completely. Okay? So he can no longer communicate to the wise people like Fabio who did not elect to cross this hypersurface r equals a. So we call the hypersurface r equals a event horizon, and we call this region here the black hole region, precisely because points in this region cannot communicate to points outside. Okay. So this is the black hole notion, and you already see it in this Schwarzschild solution once you write down the metric in appropriate coordinates that resolve this sort of apparent singularity. Okay. So, but what happens if you indeed fall into this black hole? So what happens to Mihalis? What happens to Mihalis is the following. So in finite proper time, okay, this observer, Mihalis, reaches r equals 0. And at r equals 0, you can do a little computation, and you see that the curvature blows up. Okay? So r equals 0 is in some sense singular. Now, just because curvature blows up doesn't necessarily mean you should stop the clock. And actually, the first person really to understand the geometry of the black hole interior is J.L. Singh, who is an Irish relativist. And in this paper in 1950, actually the previous quote was also from his paper, he raised for the first time this question: is it conceivable that a test particle should be able to travel through this singularity? And he very much thought that the answer to that question is yes. But it turns out that the answer is no. And the reason the answer is no is that if you think more carefully about the situation, it turns out that Mihalis, this observer here, is actually torn apart by infinite tidal deformations. So there's Mihalis a little bit later, a little bit later, a little bit later. So this is actually a completely geometric phenomenon, because you can think of my hands and legs as being Jacobi fields. And you can ask how Jacobi fields propagate along that geodesic. And the statement is that the Jacobi fields, depending on their orientation, are infinitely stretched or infinitely compressed. That doesn't follow from the fact that the curvature blows up. It is a stronger statement. So this was actually first discussed in the textbook of Misner, Thorne, and Wheeler in chapter 32.6. So that's the first reference. So there wasn't a good geometric sort of formulation of this in the literature until very, very recently. So there's a way to characterize this statement that this singularity is very, very strong without talking about particular observers like, let's say, Mihalis. And the way you can say it is the following. The space-time metric, okay, cannot be extended even as a continuous metric beyond r equals 0. So not only does the curvature blow up, that tells you that the space-time metric cannot be extended twice differentiably, but even just as a continuous metric, it cannot be extended. Okay, so this is a theorem of Jan Sbierski, and you should think morally this is actually the statement that observers are torn to pieces when they cross the singular. Okay, so this is what Schwarzschild looks like. So one way of summarizing this situation is as follows. The future may be bleak, well, for Mihalis at least, okay? But it is uniquely determined. Okay? That's to say, Mihalis will be torn apart before reaching r equals 0, and thus there is no question of what happens to him after. Okay? The theory tells us exactly what happens. Okay, so we're going to contrast the situation of Schwarzschild with the situation in another family of spacetimes that was discovered much, much later, the so-called Kerr family. So these spacetimes were discovered in 1963, if you can read here, by Roy Kerr, also fully deserving of the medal that he's wearing over there. And here is the metric. So now there's a little change of notation. You should think what used to be A in Schwarzschild is now M, and A is something else. Okay? So if A equals 0, then this corresponds to Schwarzschild with M in the place of A. So this is a two-parameter family of solutions. Still vacuum solutions and contain Schwarzschild. So again, if I don't think you can even a posteriori check that this is a solution of the Einstein vacuum equations in the time that remains. But actually, the existence of this family is very mysterious. And, well, that's has a curious story. It's the story of the discovery of this explicit family of solutions. But in any case, it is what it is. These are, again, black hole solutions, just like Schwarzschild. And moreover, they are thought to be stable solutions to the Einstein vacuum equations, and moreover, they are even thought to be the generic end state of solutions of the vacuum equation. So this is a conjecture known as black hole stability conjecture, which says that this family of solutions is asymptotically stable as a family of solutions to the Einstein vacuum equations outside its black hole region. Okay? And remember, the very fact that we can formulate this type of a statement goes back to the theorem of Choquet-Bras that says that we have a well-posed initial value problem. So what this means is I think of this family as evolving from their initial data. I perturb ever so slightly their initial data. The solution should asymptote at least outside of black hole region to another member of the family. Okay. So this is, so even though these are just some a priori, this is just some family of explicit solutions, okay? If you believe this conjecture, then these solutions sort of are stable. And in fact, these solutions, if you believe the last sentence of this conjecture, okay, everything eventually settles down to one or maybe a finite number of these solutions moving far away from each other. So it is because of this conjecture that every time we read about, black holes have been observed, etc., in the universe, then the expectation is that those black holes are described by one of these metrics. Okay? So these are really sort of the central objects, if you want, in astrophysics. Okay, so that's what happens if you're outside the black hole. By the way, maybe I'll skip this, but you can compare this statement to the sort of nonlinear stability of Minkowski space, which is sort of is a theorem in general relativity due to Christodoulou and Klein. Let me skip this. So what I'm actually interested in is not what happens to Fabio, not what happens to observers who stay outside of black holes, but I'm interested in what happens to Mihalis, what happens to observers who enter black holes. So what happens to Mihalis over here if he enters the Kerr black hole? So the point is the following. The geometry of the light cones of Kerr, when you're very far away, okay, just like in Schwarzschild, they are upright. And just like in Schwarzschild, as you move in, they turn in until you reach this event horizon, to which they are tangent, and beyond which they have turned sort of completely this way. So this tells us that just like in Schwarzschild, here we have a black hole region. Okay, so all points in this region, okay, they cannot communicate with points outside. Okay, so this is me who is falling into the black hole. But whereas in Schwarzschild, if you remember, in finite proper time, I reached r equals 0, and I was torn apart. In Kerr, these light cones, they keep on turning. They turn, sort of, they look in this depiction that they're upside down. So there is this other hypersurface to which the cones are tangent. And so what happens is before encountering any singularity, I reach this hypersurface. So this is called a Cauchy horizon, for reasons that we'll see in just a second. And after crossing this Cauchy horizon, then, well, maybe I'll see a long-lost friend coming from there. Or maybe I'll see something very bizarre. The point is, I don't know what I'll see, because sort of I'm now receiving information, I'm receiving visitors, not from initial data. You can think of initial data as being somewhere down here, but from somewhere else. So what has happened is that the solution to the equations when I'm here is no longer uniquely determined from initial data. So it's very funny because nothing went wrong locally. There are no singularities here. But suddenly, the solution is no longer determined from Cauchy data. So this is why this is called the Cauchy horizon, and this terminology is actually due to Stephen Hawking. And this is from his paper from 1966. Okay? So it is a horizon for the validity of the Cauchy problem. Okay. So remember, this is compatible with the statement as I made it of Choquet-Briard's theorem, because she only proved that the solution of the initial value problem is unique for sufficiently short time. So the Kerr solution tells you that uniqueness can suddenly fail without singularity, without problems of existence. Just uniqueness can fail because of this sort of geometric feature. Okay, so this is what gives rise to the strong cosmic censorship conjecture. So you might ask which behavior of these two spacetimes is preferable. Schwarzschild, where observers falling into the black hole are torn apart by infinite tidal deformations, or Kerr, where observers falling into the black hole live another day after crossing Cauchy horizon. It's just that their future isn't uniquely determined. So which behavior is preferable? So I guess in both Greece and the UK, we sort of like to have referenda sometime. So how many people think it's preferable to be torn apart by infinite tidal deformations? There are a few. And how many people think it's preferable to live another day, except that the future is not determined uniquely by initial data? Okay. Yeah, so not surprisingly, Kerr is in the majority. And certainly for the individual, it is better, at least if the individual in question is, Mihalis in this context, is the one who fell into the black hole. It seems infinitely preferable to sort of have to face this non-uniqueness than to know that you will be torn apart by infinite tidal deformations. On the other hand, from the point of view of bureaucracy, actually the Schwarzschild spacetime is preferable because everyone is accounted for. And the theory is deterministic. If you don't fall into the black hole, then you can observe for all time, and the theory predicts what happens for you for all time. If you do fall into the black hole, well, in finite time you are destroyed, and the theory tells you that that is what happens. And somehow in physics we are more on the side of bureaucracy, in that we want our theories to account for everybody. So should we have a second referendum? This is exactly what motivated Roger Penrose to, it was actually a very bold conjecture, to conjecture a way out of this, quote, philosophical dilemma. And the conjecture of Penrose is basically that, okay, this happens in Kerr, but Kerr is a fluke. And that the Kerr-Cauchy horizon is unstable to perturbation of initial data. So his conjecture, in modern language, is the following. For generic initial data, remember, Kerr is an explicit solution, so it is manifestly non-generic, it's symmetric, it's this and that. But suppose you had generic initial data, then what happened in Kerr could not happen. Instead, the spacetime, which is uniquely predicted by initial data, the spacetime that Yvonne Choquet-Bras gave us with her theorem, cannot be continuously extended to a larger spacetime. And by saying cannot be continuously extended, as opposed to extended with more regularity, okay, I really am saying that observers who fall into black holes are necessarily destroyed by tidal forces. Okay? So those two statements are sort of morally equivalent. Okay? So the picture should look like this, generically. So this was his conjecture. So according to this conjecture, okay, the future may indeed be bleak, but generically it is determined uniquely for as long as observers survive. So the laws of physics predict completely the future of all classical observers. So classical determinism, if you want, is restored. Okay? So this is the point of Penrose's conjecture. So now very quickly, let me tell you about this theorem that we've obtained with Jonathan Luke. So first of all, I want to emphasize that, okay, this may all sound like science fiction, but it isn't. This conjecture is a completely well-formulated mathematical question about the behavior of generic solutions to the Einstein vacuum equations, for which there is a well-defined Cauchy problem. Okay, so this is, sort of completely well-defined question, and so in particular, you can study this using the qualitative analysis of partial differential equations. It is a sort of a PD question about the Einstein equations. So here's our theorem. So remember I told you that the Kerr family of solutions is conjectured to be stable in the black hole exterior. Okay? So more about that later. So in the statement of our theorem, we will assume that that conjecture is true. Now, I'll return to that conjecture in just a second, but I should emphasize that that is not a contentious conjecture in the physics community. In fact, every single thing you ever heard about black holes in the sort of popular science literature or otherwise, it always tacitly assumes the stability of the exterior region of Kerr black holes. Okay? The whole theory that you say when people say that they look at binary systems and this and that, it all tacitly assumes this. Okay? But we will return to the status of that in just a second. So let's assume that. So then our theorem is that if the exterior is stable, then so is the interior in the following sense. So this Cauchy horizon is indeed stable, sufficiently so that observers falling into the black hole are not destroyed. Okay? So here is the observer, not destroyed, gets through. And moreover, the gets through means that the space-time is continuously extendable beyond. So that's our theorem with Jonathan. It was posted 2 years ago, almost 2 years ago on the archive. So in particular, a corollary of this is that if you believe this non-contentious conjecture that Kerr is stable in the exterior, then the original formulation of strong cosmic censorship is in fact false. All right. So what is to be done? Recall this black hole stability conjecture, so that the Kerr family of solutions is asymptotic stable as a family of solutions to the Einstein vacuum equation outside the black hole. So obviously one thing that has to be done is to prove this conjecture. So proving this would make the previous theorem unconditional and definitively falsify strong cosmic censorship. So this will certainly be proven in the next period. I mean, there's been a lot of work over the last 15 years by the mathematical community in trying to show this, and now all the things you need in order to prove this theorem are on the table. So this is certainly going to be proven. There have been many partial results. There's sort of been an analog of this proven with positive cosmological constant. There have been sort of the linear version of this has been studied, etc. So this is something that is going to happen very soon, and in particular will make the theorem unconditional. But there's another thing that can and should be done, which is the following. So remember, I told you that our theorem is a stability theorem because it says that the Cauchy horizon is stable. There's still a Cauchy horizon. And moreover, the metric still extends continuously beyond. Now in Kerr, the metric did not only extend continuously beyond, it extended smoothly beyond. In Kerr, remember, nothing strange happened at the Cauchy horizon. Well, our theorem is compatible, and in fact the proof suggests that although the Cauchy horizon is stable from this sort of coarse-grained point of view, okay, then sort of if you look at higher regularity, okay, the Cauchy horizon becomes singular. Okay? Weakly singular, so sort of not nearly as singular as the Schwarzschild singularity, because the theorem says that it isn't, but singular nonetheless. So our theorem is compatible with that possibility. So the conjecture is that indeed, for generic initial data near Kerr, the Cauchy horizon is weakly singular. So in particular, what this would say is, though spacetime is continuously extendable beyond, that's what we proved, it cannot be extended as a solution to the Einstein equations. And in fact, you expect on the basis of our proof, not only that you cannot extend as a solution, as a classical solution to the Einstein equations, that's to say as a twice differentiable metric, but you cannot extend even as a generalized solution to the Einstein equations. So one actually expects that the metric is not in the Sobolev space H1 lock at the Cauchy horizon generically. So this would be very nice to prove, because what this would tell us is that a revised, weaker formulation of strong cosmic censorship may in fact be true. So even though sort of stick figures like me can get through this Cauchy horizon, what this is actually telling you is that anything governed by a field theory, okay, even if you allow it to be governed, or you think of it as a generalized solution to field theory, it breaks down. So in some sense, a positive resolution of this conjecture would restore some form of determinism to the Einstein equations. So that's what's left to be done, and maybe someone in the audience will make progress on these conjectures. Thanks a lot.
Thank you very much. It was really a beautiful, fascinating talk, and okay, I just leave the possibility to question on people that want to.
The interesting thing is what we never had in the presentation of the theory, just the very first part that you have considered. How did you call it? A crash? You called the words to introduce the general relativity theory.
Sorry, I didn't hear?
No. In presentation of the theory of general relativity, I have hardly heard the role of the principle of equivalence in the formulation, a substantiation of the theory.
Yeah.
Which is something surprising, because the general relativity theory is a big theory. It's a theory which requires a huge amount of mathematics. But still, from the physical point of view, this theory relies on a very simple phenomenological aspect, the equivalence principle. So people have tried in all possible way to prove or to consider cases where the principle of equivalence is violated. Because if that is the case, then one has to say goodbye to the theory. Okay. But fortunately, this never happened. So the theory is also stable from this point of view. But I never heard about that.
Well, I mean, you can see, if you want, let's go back. I mean, in some sense, this is more a historic point, but it's worth making, certainly. Right, so you can already see, right, the equivalence principle here in the Newtonian theory. Basically, the equivalence principle is that, well, this m here is the same as this m here. So in particular, sort of in, if you think of sort of, if you think of this x as not counted in the sum here, all right, then the motion of this test particle in the gravitational field given by these masses, okay, does not care what is the mass of the test particle, okay, because it cancels. And this, of course, sort of motivates the expectation or the hope that you can describe in the test particle. I've gone further. In the test particle approximation, you can describe gravity geometrically. That's to say, you don't, it doesn't matter what is the mass of this particle. It's sort of independent of its mass as a freely falling particle. It is traversing a geodesic in space-time. So, I mean, if you want, the sort of, this is precisely the type of consideration that sort of led Einstein to formulating what we now view as sort of a geometric theory. So it's sort of, it is built in to to the structure of general relativity. Now, of course, at the end of the day, there were the considerations that led Einstein to the theory are not the same things as, now the epistemological status of the theory is much, much stronger than, whatever ideas led Einstein originally to the theory. So somehow we don't, the reasons that we believe in general relativity are now very independent from, those type of considerations per se. But in any case, certainly as a heuristic to being led to this structure, the fact that Einstein sort of believed that this cancellation is fundamental, this played a big role. It's sort of clear. But somehow, finally, it is not, if you want, even in general relativity, the final formulation of the theory, let me use the modern notation, is this. That's to say, this is the theory. It is this. So, the geodesic approximation, in which, let's say, you can see the equivalence principle, all right? It follows from this, and it is true only to the extent that it follows from this. So somehow the theory is no longer understood in terms of sort of things like equivalence principle or this and that. The theory really is governed by this. This is more fundamental than equivalence principle. So equivalence principle is only true to the extent that it follows from this, because by definition, this is general relativity.
Okay, there are other questions or remarks?
What is known about the stability in the case in which you put an infinitesimal amount of matter inside somehow the...
Well, then there is an interesting problem. So, for instance, and it's really only been studied in the case of Minkowski space. So I mentioned, well, I sort of skipped this slide, but let me show it again. Right. So in the case of flat space, it's a theorem that sort of flat space is stable. So sort of Minkowski space of special relativity is stable in general relativity as a solution to the vacuum equations. Okay, so this was the theorem of Christodoulou and Kleinerman. But this has been generalized in the case that you have various forms of matter. So for instance, well, the simplest forms of matter to consider is electromagnetic fields. So in general relativity, we usually think of those as matter. Scalar fields, but also Vlasov fields, so collisionless matter. So in all those cases, sort of there's an analog of this theorem where you also include such matter fields on the right-hand side of the Einstein equations, and of course then you have to couple the equations with the equations of motion for the matter. So in the black hole case, that becomes, well, in the electrovacuum case, one certainly expects a similar theorem. But for sort of, let's say even for Vlasov matter, which is a popular matter model because actually it has some sort of degree of, it has some regime of validity even in galactic dynamics is considered, but also it's a clean sort of matter model that you can certainly try to mathematically study. It's much more difficult to understand stability. And the reason is that, well, you can have matter sort of forever orbiting your black hole. And sort of the methods that we have in sort of nonlinear wave equations in order to understand stability, they really need that you prove asymptotic stability. So you really have to understand very well the possible asymptotic states. And the reason that the stability of black holes will be shown is that, well, the asymptotic states are just this finite dimensional sort of class of states, namely the Kerr family. But if you also have matter, and all of a sudden you have sort of a big zoo of stationary solutions where you have a black hole surrounded by matter, then the methods that we have to, even if you believe that these are stable, let's say orbitally, the methods that we have for showing that unfortunately are not there yet. So that's of course a very interesting problem and one for the future.
Thank you, Mihalis. And are there other questions? Okay, if not, let me thank you again warmly, Mihalis. Okay, now there is a refreshment at the 7th floor as usual.